I'm Jess Enright. I work in the School of Computing Science at the University of Glasgow. I'm a senior lecturer here, and I'm going to talk about the Firefighter game on a network, which is an example game that I use in my teaching, both in level 1 and upper year honors courses. It's also in my research, which involves looking at networks and spreading processes, by which I mean things like diseases or like rumors or like ideas spreading over a network. What I mean by network really is dots, where some of the dots are joined up by lines. And when we think about something spreading, you might think about like a meme spreading over Twitter, where the dots are the people on Twitter and the lines are the follower relationships between them. I work on this from an infectious disease perspective mostly, so controlling diseases that people can catch, Mpox, COVID-19, other diseases like that. But as I say, I also use this in a more theoretical way in my teaching. And the example I want to talk about is the Firefighter game, and I want to show you that first as an example. So this is my example of the Firefighter game. We have a network here, so we have some of these dots joined up by lines, and some of the dots are not joined up by lines. What we have here is a red dot, and that's meant to indicate that a fire has broken out on this network. The fire is going to spread over every possible link that it can every turn. But the network is not doomed because it has us. We're firefighters. We're trying to defend this network. So what's going to happen is we know the fire has started here, and then we get on our turn, we get to pick a dot and defend it, and then the fire is going to spread over all of the links that it can spread to. It can't spread to something that we've defended, but it can spread to everything else that is connected to something that's burning. There we go. Things that are on fire in this game stay burning forever, and things that are defended also stay defended forever. So we've done one step of this game, and now it's our turn to defend again. We think about where might we want to defend to try and save as much of this network as possible. So here's probably a pretty good choice, down here. We could think about other places, up here maybe, but if we defend up there, we're only saving this one dot here. It doesn't save anything else. So this is probably a pretty good choice, down here. Now, the fire gets to spread again, so it's going to spread across these two lines. There we go. And now it's our turn to defend again. There's only one sensible place to defend, and it's here. And the game is over because the fire can't spread anymore. So in this game, we often want to ask things like, how much of the network can we save? Can we save particular parts of it that we care the most about? Often in computing science, we're interested in these sorts of questions. We call these optimization questions, where we're trying to find the best way to solve something, the best possible outcome. So what we want to do on these networks, usually, is find the best possible way to defend the network. And it turns out that finding the best possible strategy is a really, really hard problem. So what I'm going to talk about for the rest of this lecture is to convince you that we can't just do a brute force try everything approach, and then convince you that there are other things that we can do to try and work around it. So let's talk about the brute force approach first. As an algorithms person, so I work on these sorts of optimization approaches, one of the things that I often hear from people is about how fast computers are getting. And because a computer is faster and because we have modern computers, doesn't that mean we can just try all the possibilities? Just try all the possibilities and find the best possible answer that way, or something like it. So I'm going to spend a little bit of time trying to convince you that no, this is a very bad idea and you cannot do this in many cases. So the way I'm going to do that is talk to you about what it would mean to look at all of the possible defending strategies. So remember in that game, we picked dots to defend, right? When we're picking dots to defend, we did them in a particular order. So one way that we could think about looking at all the possible defense strategies is to look at all of the possible orders of the dots. So if we have one possible set of defenses in a particular order, that's kind of like one strategy, right? So if we could look at all of those, we could test each of those, and we could see which one comes out best. This, it turns out, is not really feasible. So, for example, on a network with 5 dots, how many different orderings do you think there are of the dots? There are 125. So we have a mathematical expression for this. It's factorial. So it's 5 factorial. That's actually not so bad. You can probably look at all of those on any reasonable computer in a reasonably quick time. If you move up to 10 dots, so that's just a doubling of the number of dots, we go from having just over 100 possible orderings to having about 3.5 million possible orderings. So that's already getting pretty big, right? 3.5 million possible things we need to try out. Probably lots of modern computers, we could do that in reasonable time. That's not crazy, but that's only 10 dots. If we move up to 15 dots, then we have over a trillion possible orderings, which is a very big number. That's probably at the edge of what's possible for even, very expensive computation, right? Over a trillion possible strategies to check out. But if we get up to even like a modestly but medium-sized network, like 100 dots, if you think about it, 100 dots is really not that many. Like if I'm thinking about the social connections between people in one of the courses that I lecture, This has got 150 people. So this is even smaller than that. Looking at the connections between 100 neighborhoods or 100 people, we probably in practice want to do it on much bigger networks than that. But even 100 dots, how many possible strategies are there? How many possible orderings of the dots? There's a number that is so big that I'm not even going to attempt to say it. It's got like 158 digits. It is a number that is bigger than the number of atoms that exist in the universe. So it's way too big. We can't possibly look at all of those strategies, even on the best computer available. So all I'm trying to do there is convince you that when you try this brute force try everything approach, the number of things you check gets so big, so fast, that it's really not feasible to do. But lots of times we can't just throw up our hands and give up and say, oh, we can't solve this problem computationally. We need to do something about it. So what I'm going to do for the rest of the time is talk about a couple different approaches that we use when we can't check all of the possible strategies and we can't find the best possible answer. So the first one is restricting what kind of network we're looking at. This is one I use a lot in my research, in kind of complicated ways, but even in some simple ways. So just because we can't find the best possible strategy on any network, there are probably some networks that even though you've just learned the game, you can come up with the best possible strategy on it. So this one is one of them. It's a path. It's just a bunch of dots joined up in a straight line. If a fire breaks out somewhere in the middle of that path, you can probably work out the best thing to do. It's defend just beside the fire, and then this fire will spread once, and then you defend just the other side of it, and the game is over. Only 2 things have burned. That's the best that you can do. And you know that, right? Just because the problem is in general too hard to solve doesn't mean you can't solve it on these particular cases. There are cases that are a little bit more complicated that you can still figure out the perfect strategy on. So another one is a cycle. So path is just a straight line of vertices or dots, but a cycle is just like it sounds, like a circle of them. And the strategy there is very similar to the one you use for a path. You defend right beside the fire, and then you let the fire burn one, and then you defend just the other side. So on that kind of restricted input, you can come up with the best possible answer really easily. If you thought about it for a bit, you could probably even come up with a pretty good answer on something that looks a little bit more complicated like this, which is a tree, we call it. So this is a network that doesn't have any cycles in it. It can have lots of branches, but no circles. So on this kind of graph, on certain kinds of trees, we can solve this problem. There is a way to find the best possible defense for a fire that breaks out, with some slight restrictions on the tree. And that takes what we call n cubed time. So if we're looking at a tree of 10 dots, we only have to do 10 to the exponent 3, so 10 times 10 times 10 possible computation steps. Instead of, remember, 10 factorial was like loads more than that, right? So my point here is that if you can restrict the kind of network you're looking at, sometimes you can use special reasoning on those types of networks to solve your problem exactly. So that's one way to do it. But even when you need to solve your problem, and you need to solve it on networks that are not these particular special kinds, you need to solve it more generally, there are still approaches you can take, which are either not guaranteed to get you the best answer, but usually get you a pretty good answer, or are guaranteed to get you the best answer, but might take a really long time, right? So those are the last 2 things I want to talk about because I use those in my teaching. I use that first one in my first year teaching sometimes as an example of how we think about coding up algorithms and general rules. And I use that second one in my honors teaching on general solvers. So let's talk about this general rule approach. We call these heuristics. And the idea there is that you have a rule that helps you find an answer that is usually pretty good, but we can't necessarily guarantee how good it is. These people are pretty good at coming up with, actually. I bet if you sat and you thought about this game for sort of 5 minutes, you'd come up with some really good rules. Most people do, right? So if you look at a network where things are really uneven, and there are some dots with lots of connections and some dots with very few connections, probably you'd guess that you should defend those dots that have lots of connections. Most people figure that out pretty quickly. There are other general rules, like often you want to defend things that are near the fire instead of things that are very, very far away. That's another one of these heuristics. So these sort of rules can usually find us an answer that is pretty good, but we can't guarantee how good it is. It might be really bad. It's usually in practice pretty good. But the big advantage of this sort of approach is that it runs super fast, really, really fast. So there the trade-off is the answer is less reliable, but the computation is really, really fast. The other approach is about general solvers. And this is what I teach more on my honors course. So these are approaches where the trade-off goes the other way around. We can guarantee that the answer is the best possible answer, But in the worst case, it might take a very, very long time. We can't guarantee that it's going to be much better than brute force, because really, general solvers are doing like a fancy version of brute force, where they try and do some smart reasoning about which things they don't really need to check. But again, that trade-off is the other way around, guaranteed to give us the best possible answer, but might take a long time, though in practice usually goes pretty quick. So in my honors level teaching last year, I had my students code up the Firefighter problem as one of their assignments to run in a general solver, to test out different kinds of solver techniques and see which one was faster on this kind of problem. I think they had a lot of fun with it. Thank you so much for listening. I really hope you've enjoyed it. And if you'd like to learn more about networks and algorithms, I hope to see you at the University of Glasgow.